Hey guys, chapter 5, probability. And this time it's independence and multiplication rule. So two events E and F are independent if the occurrence of event E in a probability experiment does not affect the probability of event F. Two events are dependent if the occurrence of event E in the probability experiments affects the probability of event F. So we'll see a couple of examples here. All right, suppose you flip a coin and roll a die. The event of obtaining heads and rolling a 5 are independent because the results of a coin flip do not affect the results of a die toss. And actually, they're all independent events. The probability of you rolling a 5 does not affect you rolling a 6. So all of those are independent events. B, are the events earn a bachelor's degree and earn more than 100,000 a year independent? No, because knowing an individual has a bachelor's degree affects the likelihood of the individual earning more than 100,000 a year. So a bachelor's degree does increase your odds of making 100,000 a year versus people that don't. There are a couple of things that you could do to earn 100,000 a year, but earning a bachelor's degree does increase your odds a bit. And C, two 24-year-old male drivers who live in the United States are randomly selected. The events male 1 gets in a car accident during the year and male 2 gets in a car accident during a year are independent because the males are randomly selected. Those two males are independent unless one of them went specifically looking for the other just to hit them. These two are independent. This means what happens with one of the drivers has nothing to do with what happens to the other driver. Another thing that we could say to make it a dependent event is the likelihood of one of those 24-year-old men driving over 100 miles an hour might increase the odds of them getting into a car accident, because at that point you're considered a reckless driver and you might get in an accidental car accident. Disjoint events versus independent events. So disjoint events and independent events are different concepts. Recall that two events are disjoint if they have no outcomes in common. So that is, if knowing that one of the events occurs, we know the other event did not occur. Independence means that one event occurring does not affect the probability of the other event occurring. Also, disjoint events happen with one probability. With independent events, we're looking at the combination of two different probabilities. So we're just looking at, for disjoint, we're just looking at one event happening. So just one event. And with independent events, we're looking at multiple events. So multiple events. So one event happening versus multiple events happening. So that's our probabilities. And let's keep going. So therefore, knowing two events are disjoint means that the events are not independent. Yeah. All right, use the multiplication rule for independent events. So here we have the multiplication rule. If event E and event F are independent events, then the probability of event E and the probability of event F are equal to probability of event E times the probability of event F. So in the game of roulette, the wheel has slots numbered 0, 0, 0, and 1 through 36. A metal ball rolls around the wheel until it falls into one of the numbered slots. What is the probability that the ball will land in a slot number 21 2 times in a row? So what we're looking at here, remember the formula, it's probability of event E and probability of event F equal to probability of event E times probability of event F. So the product of those two. So here what we're asking is, what is the probability of landing on the slot numbered 21? So probability of 21 and probability of 21, which means it's going to be the probability of 21 times the probability of 21. So here what we have is 21. So only one of those slots is number 21. So looking at the probability of any of these, it's the number of ways to get that solution divided by the total number. So number of ways to get that solution is 1. There's only one labeled 21. And out of 36, then 37, 38 for the 0 and double 0. So that's 1 out of 38. And that's for probability of 1, I'm sorry, probability of 21. And now for probability of 22 or 21 again, it's the exact same thing. So here, when we're multiplying fractions, we could just multiply across the top and multiply across the bottom. So 1 times 1 gives us 1. And 38 times 38, let's take it over to Excel. Another way we could do this is just multiplying the two. So looking at probability of 21, we said that's equal to 1 over 38. Perfect. So now the probability of 21 and 21, that's equal to the probability of 21 times the probability of 21, which is a probability of 21 times a probability of 21. And that's our solution. So 0.0006925. So multiplying that by 100, we have a 0.069% chance of actually getting this sort of result. So the chances of this are very, very slim, so very unlikely. And let's see what they say. So 38 possible outcomes of the probability of landing on 21 is 1 out of 38. Cool, that's what we got. Because the events 21 on spin 1 and 21 on spin 2 are independent, we have probability of 21 on spin 1 times the probability of 21 on spin 2 equaling the exact same thing. So 1 over 1,444, and that gave us that solution that we got on Excel. Perfect. So we expect the ball to land on 21 twice in a row, about 7 times in 10,000 trials. So if we run this 10,000 different times, we expect that sort of thing to happen only 7 times. So now multiplication rule for n independent events. So very similar to to the other probabilities that we talked about in the last section. If we have independent events or with disjoint events in the addition rule, we have independent events in the multiplication rule. So if we have n independent events, then the product of all of them, or then the probability of each of those happening. So probability of event 1 and probability of event 2 and probability of event 3, all the way up to probability of event n, then the product or the probability is equal to the product of each of those. Probability of event e, or probability of event 1 times the probability of event 2, all the way to the probability of event n. So looking at this, the probability that a randomly selected 24-year-old male will survive the year is 0.9986. So according to the National Vital Statistics Report. What is a probability that 3 randomly selected 24-year-old males will survive the year? So What this value here is probability of survive. That's equal to 0.9986. And now what the question here is asking, what is the probability that 3 randomly selected 24-year-olds will survive? So what's the probability of survive time and the probability of survive and the probability of survive? So here, because we have 3 independent events, we can multiply them together. So probability of survive times the probability of survive times the probability of survive. And now from here, let's do a little bit of algebra. But since we have the exact same thing multiplied 3 times, what we could do is actually just say probability of survive. And we could raise whatever this value is to the power 3. So let's bring it back over here. We said the probability of survive is 0.9986. So now the probability of 3 surviving, that's equal to the probability of survive raised to the power 3. So equal to the probability of survive. Could do a little caret or shift 6 raised to the power 3. And this is our solution. So probability of 3 randomly selected 24-year-old men surviving is 0.9958. And notice that it is lower than this up here. This is the probability that they will survive that given year. And this is also the probability that they would survive that given year. This one's lower because we're looking at 3 different people surviving. So the likelihood of 3 people surviving is going to be lower. The likelihood of even 10 people surviving, so probability of 10 survive, that's equal to this raised to the power 10. So here it went down a whole percentage point from what we originally started. So going down an entire percentage point makes it less likely that we randomly select 10 people that would survive. If we randomly select 100 people that survive, those probabilities are going to get a lot smaller. So let's come over here and see if we missed anything. So all 3 survive. Yep, that's what we got, 0.9958. So if we randomly select 3 24-year-old men 1,000 different times, we would expect all 3 of them to survive 1 year in 996 of the samples. So again, if we randomly go and put a little, not tag, that's me, but if we randomly look at 3 people or 3 24-year-old men and 1,000 different times, so that would be 3,000 different people, we would expect all 3 of them to survive 996 times. All right, what is the probability that 20 randomly selected 24-year-old males will survive? So very similar to the way that we did the last one. So we set the probability of survive is equal to, I forgot what that value was, 0.9986. And this time we're looking at the probability of 20 randomly selected 24-year-old men surviving. So probability of 20 surviving. So we could automatically jump to that second part, that second equation that we wrote. So this would be the probability of, wrote that wrong, probability of surviving 20 times. So raising it to the power of 20, because we should have 20 of those same probabilities. And since we know the probability of survive, we could just say 0.9986 raised to the power of 20. And let's see what that gives us. So here, probability of 20 survive. That's equal to this value raised to the power of 20. And it gives us that. So another way we could do it is just by typing it in just like that. So equal to 0.9986 raised to the power of 20. And exact same numbers there. So whichever one you want to use, you could use. But that's it there. Oh, I didn't even get that number. 0.997236, so 24. So 9724. .9724, perfect. So they had this, the first one all the way up to the 20th one, and notice that just kind of progressing the way that we did it. So probability of the first one surviving, probability of the second one surviving, all the way up to the probability of the 20th person surviving. So all of those, we know that there's 20 of them. So same thing here, 20 of them. Well, 20 of these products here. And that's how we're able to say this. That's how we're able to say 20 right here. And from there, we ended up with our solution once we plugged it into our calculator. So if we randomly selected 20 24-year-olds 1,000 different times, we would expect all 20 of them to, or we would expect all 20 of them to survive in 1 year in 972 of the samples. Okay, so next we're going to compute at least probabilities, and let's see, so compute the probability that at least one male out of the 1,000 aged 24 years old will die during the course of the year if the probability that randomly selecting a 24 male survives that year is 0.9986. Okay, so looking at this probability, the best way to see it is if we have like a smaller sample, so that way you guys could see exactly what's going on. So if we have, let's just use a sample of 3. So 3 males. So looking at this, so 3, it's the same males that we're talking about in this equation or this example. So 3 males. So the probability that they either survive, live or die, we'll use those words. So L for live and D for die. These are all the different possible ways. So we have the first one is that they all live. So 1, 2, 3 lives. And then the first 2 live, the last one dies, live, die, live, die, die. So that's all the different possibilities of the first one lives. And now for the first one dies, so we have die, live, live, die, live, die, 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 live, and die, die, die. So we have those 8 different possibilities here. And out of these 8, we're looking to compute the probability that at least one out of the 1,000 aged 24-year-old will die. So at least one dead. So here, do we have at least, or we're going to highlight the ones where we have at least one dead. So the very first one, everyone lives, so no one's dead. There's at least one death here, at least one death here, 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 and here, all of them pass. So at least one dead is that very first one. And instead of looking at each and every one of these other ones, instead of grabbing 1, 2, 3, 4, 5, 6, 7 different probabilities, computing those, adding all of those together, we could use our complement rule and just figure out what this is and find the complement of that. So in other words, the probability of 3 deaths, no, I'm sorry, the probability of at least 1 death out of 3, that's going to be equal to 1 minus the probability of 3 people living. So the probability of 3 of them, all 3 of them living, is going to be the complement of at least 1 death. So here we could just plug in these numbers or that number there instead of the 3, throw out that 1,000. And we could see how it makes it a lot easier computing it that way. So again, probability of at least 1 death out of 1,000. That's equal to 1 minus the probability of 1,000 living or 1,000 surviving. And again, the probability of surviving, or in this case, I keep using living and dying. So probability of living is equal to 0.9986. So let's take this to Excel. All right, so probability. So we're looking at the probability of at least 1 death out of 1,000. So that's going to be 1 minus, let's stretch this one out a little bit. All right, so this is going to be 1 minus the probability of 1,000 that live. So now looking at that, we said that the probability of living or surviving that year is equal to 0.9986. And now the probability of 1,000 living, that's equal to this probability raised to 1,000. There we go. And now to find the probability of at least 1 death out of 1,000. That's equal to 1 minus the probability of all of them living, which is this. And there we go. So the probability that at least 1 person dies out of 1,000 is a 0.753 or 7536. So 7536% chance of them dying, or at least 1 death. And let's write it down just so we have it. So at least 1 death out of 1,000 is equal to 0.7536. And there we go. Let's see if we missed anything. So 0.7536, perfect. So they looks like they did something really similar. So they kept it all in one problem and they just solved it from there. So I kind of bounced around from one place to another, but looks like they ended up with the exact same answer. All right, so now if we randomly selected 1,000 males aged 24 or 24 years of age 100 different times, we would expect at least 75 of the samples to end up with at least 1 death. And now we have a little summary. So the probability of an event is between 0 and 1 inclusively. So it'll be 0 less than or equal to the probability less than or equal to 1. The second part, these are two conditions. So the second condition, the sum of the probabilities of all the outcomes in the sample space must equal 1. That is, if the sample space S is event 1, event 2, event 3, all the way up to event N, then the probability of event 1, of event 2, all the way up to event N is equal to 1. 3, if E and F are disjoint events, then, so remember, disjoint events is different from independent. Disjoint is our sample space, and we have two disjoint. Not one value falls into both of the categories. So if event F and E are disjoint events, then the probability of E or F is equal to the probability of E plus the probability of F. If E and F are not disjoint, then we have the probability of E or the probability of F equaling the probability of E plus the probability of F minus the probability of E and F. And the reason why we have that is because we have these two here. If they have these things here in common, they're being counted twice. Once because of this first event and twice because of this second event. So we have to subtract at least one of them so that way we could clear that overlap. If E represents any event and E complement represents the complement of E, then the probability of the complement of E is equal to 1 minus the probability of E. So that's what we're calling our complement rule. So it's just 1 minus the probability of the other one happening. If E and F are independent events, then the probability of E and F is equal to the probability of E times the probability of F. Notice that OR probabilities use the addition rule and probabilities use the multiplication rule. Accordingly, OR probabilities imply addition and probabilities imply multiplication. And that wraps up this section. And if you guys have any questions, don't forget to email me, but if not, good luck.